Picture this. You're firing up a massive, multi-million-dollar LED video wall for a live broadcast. And instead of a pristine, flawless image, you get completely inverted colors, scrambled pixels, and just ugly ghosting lines everywhere. I mean, it's a total visual disaster, right? But what if I told you that the ultimate hero that fixes all of this and actually prevents it from happening in the first place is just a single, meticulously crafted file? Welcome to The Explainer. Today, we're diving into a masterclass on the LED receiver card configuration blueprint.
Okay, let's dive right into this. The receiver card is essentially the brain behind the beauty of literally any LED display. It's the hardware living inside the LED cabinets, and it tells the individual LED modules exactly how to behave. It's totally responsible for translating that incoming video signal into perfectly timed electrical pulses that actually create the image you see. When you're creating a receiver card configuration file, you're basically giving this brain its operating instructions. A proper configuration ensures the correct resolution, perfect color mapping, the right refresh rate, and optimal brightness. Without it, or, if the wrong file is loaded, the hardware literally doesn't know how to map the pixels. And that is exactly how you end up with those terrifying inverted colors.
So, here's our roadmap for today. We're going to cover 1. Preparation and initial setup. 2. Decoding module naming. 3. Automated intelligence settings. 4. Refresh rate versus grayscale. 5. Fixing fade and ghosting. And finally 6. Verification and final save. All right, let's kick things off with Section 1, Preparation and Initial Setup.
Before we even think about touching the heavy software engineering side of things, we have 3 mandatory pre-debugging steps to get our digital and physical environments perfectly aligned. First up, you've got to set your control computer to copy mode, or duplicate display. Second, and this is absolutely critical, you must match the transmitter card resolution exactly with your computer's graphics card resolution. And third, you need to physically confirm your lamp panel type, the pixel pitch, driver chips, decoding, and the scanning mode. Honestly, skipping these steps just leads to mismatched scaling and immediate display failure, so don't skip them.
Looking at this in practice, a technician preparing for intelligent settings would specifically set both the PC graphics card and the sending card to a matching custom resolution. Something like 1366 by 768, for instance. By forcing a 1-to-1 pixel map right at the source, you completely bypass the risk of the operating system trying to stretch or compress your video signal before it even reaches the LED wall. Moving right along to Section 2, Decoding Modulo Naming Conventions.
So before the software can do its job, we really have to decode the physical hardware. If you check out the exact label printed right on the printed circuit board of a module, it usually looks like a completely random string of text and numbers. But it's not. It's actually a complete map of the module's DNA. Let's break down a standard naming convention step by step. Say you come across a label that reads P32121 64x6432S V1.0. Here's exactly what that means. P3 instantly tells you it has a 3mm pixel pitch. 2121 is the physical size of the surface-mounted lamp beads. 64x64 is the exact pixel resolution of this single module block. 32S means it uses a 32-scan time division multiplexing ratio. Basically, it lights up 1/32 of its rows at a time. And V1.0, well, that's simply the version number. Once you can read this, you know exactly what kind of hardware you're dealing with. Now contrast that with a custom module name, something like UNI U1980 9030 SV3.0. Here, UNI is the company prefix, U19 stands for a superfine 1.9mm pitch, 80x90 gives you the irregular resolution, 30S is a 30 scan mode. And what about that extra 3 right before the S? That indicates there are 3 distinct RGB datasets being input. Knowing how to read these specific custom tags is really what separates a novice from a true expert technician. Next up is Section 3, Automated Intelligence Settings. Welcome to the automation phase. This is where the software essentially acts as your highly intelligent assistant. So, what is intelligence setting? It's a guided software workflow that automatically detects all those complex module parameters. Instead of manually typing in thousands of lines of data, the software probes the module to identify the specific driver ICs, like the advanced MBI 5153 chip, for example, and it automatically sets the appropriate decoding, like the 74HC138. Honestly, it saves hours of tedious manual entry and drastically reduces human error. Think of the workflow as a dialogue between the technician and the software. You start the intelligence setting, and the software lights up the physical module.
As the module flashes red, green, and blue in sequence, or displays specific lines, you, as the technician, watch the physical board and click to confirm what you're seeing in the software. By verifying the color sequence and the number of flashing rows, you're manually confirming the software's RGB mapping and its scan mode deductions.
All right, Section 4, refresh rate versus grayscale. This is a big one. Pay super close attention here because this is arguably the absolute peak of LED configuration. First, we need to draw a hard, distinct line to clear up a massive industry misconception. Frame rate is a property of the input signal, like a 60 frames per second feed coming from your video source. Refresh rate is entirely different. It's a property of the physical hardware output. It's the rate at which the LED driver IC updates the physical pixels, which for a professional display is typically between 1920 and 3840 Hz. So each input frame is actually multiplied and displayed dozens of times by the hardware. So the crucial point comes down to a strict mathematical limitation. Think about this equation. Refresh rate times 2 to the power of grayscale bits must be less than or equal to the driver IC's internal clock frequency divided by the scan groups. I know, it's a mouthful, but this physics equation is basically the holy grail of LED configuration. It proves unequivocally that you cannot maximize both refresh rate and grayscales simultaneously. You have a fixed clock budget, and you have got to spend it wisely. Let's look at a concrete example of this trade-off in action. Imagine a driver IC with a 33 MHz clock in a 1/8 scan module. If you try to aggressively push your refresh rate to 768 Hz, the math literally forces your grayscale depth to drop to 10-bit. You will immediately see ugly, blocky color banding in smooth gradients, like a picture of a blue sky. But if you balance that refresh rate down to 1920 Hz, which by the way is still plenty fast enough to eliminate scan lines on camera, you free up the clock cycles to achieve a beautiful, smooth 14-bit grayscale. This is especially true if you're using advanced PWM chips, which can handle smoother motion for sports broadcasts much better than standard general chips. Moving into troubleshooting territory with Section 5, fixing fade and ghosting. Even if you perfectly balance your refresh rate and grayscale, the laws of electricity can still introduce annoying visual artifacts. The primary culprit here is parasitic capacitance in the PCB layout, which causes residual brightness, commonly known as ghosting. If you put high-contrast text on the screen and see these faint ghost lines trailing above or below the letters, you've got a fade issue. To fix this in the configuration file, you engage the software's discharge processes for upward remaining light, and you activate pre-charge pulses in the IC for downward light. If the interference still persists, slightly lowering the clock frequency, say from 13.9 MHz down to 12.5 MHz, will very often completely stabilize the image without visibly hurting your overall performance. And finally, we arrive at Section 6, verification and final save. In the world of high-end display engineering, no job is truly done until it's saved, mapped, and fully verified. Once your parameters are dialed in, you must save this configuration to a local .rcfgx file or a USB drive for quick on-site deployment. But before you walk away, you have to verify. If you happen to notice a cabinet with scrambled pixels just because a physical ribbon cable was wired backward, you can use the Data Group Exchange feature in the software to digitally remap the data and fix it instantly without even touching a screwdriver. Then you throw up a full, uniform white test pattern. If you see no visible seams, perfect color balance, and smooth video motion, well, you've succeeded. We've covered the complete journey today, from physical hardware decoding all the way to the most advanced software parameter modifications. But I want to leave you with this final thought. Knowing the unbreakable mathematical law that you literally cannot have both maximum refresh rate and maximum grayscale at the exact same time, how will this crucial engineering trade-off change the way you evaluate, purchase, or configure your next LED display setup? The power is entirely in your hands now. Thanks so much for joining me on this explainer. Keep learning, keep optimizing, and I'll catch you next time.